All right, let's come back. Okay, so let's continue with this problem. So this region R is rotating about the y-axis. Then we obtain the solid, but the inside part is empty and with a solid looking like a cylinder, right? Cylinder. So that is the solid. Try to imagine the solid in 3 dimension. Okay. Then how can we evaluate the volume of this solid? We are going to use the Shell's method. Okay, we are going to use the Shell's method. Let's work out step by step. Okay, let's work out step by step. So how can we get the shell? How can we get the shell? So here, this is still, again, let's check the region. So this is the region under the curve fx from A to B. Like the area, like the estimate approximating area we did, we will cut this region into n strips, right? N strips, and using n approximating rectangle area to estimate the area of the strip. So that is the same idea we did here. Okay, so number one, subdivide the interval, subdivide AB, the closed interval AB, into n subintervals. So subdivide the closed interval AB into n subintervals, and we can form those subintervals, right? So let A equals x0, right? x0 to x1, and then x1 to x2, and then the I subinterval will be xi minus 1, xi, xn minus 1 to xn, the nth subinterval, right? Like here. And with the equal weights, right? With the equal weights, how can we find the formula of the equal weights of the interval? With the equal weights, delta x, my delta x will be b minus a over n. It's the same, right? It's the same. So here we will cut the interval AB into n subintervals, and the equal weights for each interval will be delta x. How can we find the delta x? B minus a over n, right? It's the same. Now we draw here. Let's look at in the I subinterval, right? So in the I subinterval, in the interval xi minus 1, this is the I subinterval. So be careful about the notation. Okay, notation I used, this is the common notation we used through the textbook. We use some special notation when we discuss the quiz question from the Kehan class, but that is special one we used or we designed to solve the questions. Usually we will use this xi minus 1 to xi to denote the I subinterval. Okay, I subinterval. So in the I subinterval here we have the xi bar. What is my xi bar? That is the middle point. Okay, middle point. We use this notation for the middle point in the ith interval. How can we find the middle point? Middle point is xi minus 1 plus xi over 2. Okay, over 2. Now, how can we form this rectangle? How can we obtain this rectangle? So for the ith rectangle, for this ith approximating rectangle, the width is easy, right? The width is easy. The width is delta x. How about the height? How about the height? So we will take the height. We will take the height of the f. So this part gives the height. This is the height of the rectangle, right? We are talking about the rectangle so far. So the height of the rectangle will be the f evaluated at the middle point, okay? It can be left end point or right end point, but here we just choose the middle point, okay? And we know we have the sample point as a more general notation. So the height of the ice rectangle will be fxi bar, and of course the area of the rectangle is the height fxi bar minus times the delta x. No problem, okay, no problem. But we don't care about the area of the rectangle now. So what shall we do about this rectangle? So this is a rectangle. Then I will rotate this blue rectangle about y-axis, okay, about y-axis. So this shell, okay, this kind of orange color shell is obtained by rotating the ice rectangle, okay. So here number 3, the shell, and actually this is the cylindrical shell. Cylindrical shell. In this kind of orange color. The cylindrical shell is obtained by rotating the rectangle, by rotating the ice rectangle about y-axis. That is how we obtained this shell. And you can imagine that rotate this rectangle about the y-axis, we get a cylindrical shell, okay? We get a cylindrical shell. Then what is the volume? The volume for the cylindrical shell. And actually this is the ice shell, okay? We will call it ice shell because it's rotating about the ice rectangle. Then the volume for the ice shell. The volume for the ice shell. Now let's recall the cylindrical shell. The volume of the cylindrical shell let's check it, okay? Let's check it. Let me mark it as VI, okay? Which means, so that is circumference times the height times the thickness. Or you can come back a little bit, okay? You can come back a little bit. This is again the cylindrical shell, right? Cylindrical shell. How can we find the volume of this shell? How can we find the volume of this shell? So if we can figure out the outer radius, okay? If we can figure out the outer radius and the inner radius, then that will be much easier, right? That will be much easier for the ice shell. So here is we are talking about the shell, for the shell. Outer radius, let's check here, okay? So this is the center, right? This x-axis gives the centroid axis for the cylinder, either the inner one or the outer one. So the outer radius will be this length, right? I showed in the red color. That will be the outer radius. This one will be my R2 outer radius. What is the inner radius? Let me choose a different color. What is the inner radius? So from here, the circle we draw, the base circle we draw, this one gives the inner radius R1, right? So of course here you will check that the outer radius R2, R2 actually is XI, right? R2 is XI. What is R1, the inner radius? Actually, the inner radius is the left endpoint of the subinterval, of the I subinterval. So outer radius R2 will equals the right endpoint xi. The inner radius will be the left endpoint xi minus 1, right? And then what is the R we defined? What is the R we defined? So the R will be the average. Let me come back to the red color. Okay, let me come back to the red color. Sorry. Just a little confused about the color. So what is the R? The R will be the average of the outer radius xi plus xi minus 1, right? And again, what is the formula? What is the formula here? You can check that. You can check that. Actually, the average of the left and the right endpoint for the ice interval, that is xi bar. So my R actually is xi bar, right? And delta x is delta R, sorry, delta R we called will be the difference xi, the outer radius minus the inner radius. So actually the delta R is the weights for the ice interval, and all the weights will be the same, which is delta x. So let's recall the volume for the ice shell. The volume of the ice shell, use those notation we did before. That will be 2 pi r, the circumference of the circle with the radius r, times the height for the shell, and then times the thickness delta r, right? Let's recall the previous formula. Circumference times the height times the thickness. Now what is my r? My R actually is the xi bar, right? They are the same. They are the same. My R is xi bar. What is the H? Let's write it delta R first. What is delta R? Delta R is the same as delta X. That is the weight for the each subinterval. What is the height H? So from here we can check that this one gives the height. Actually, the height of the ice shell is the same as the height for the rectangles. So what is the height for the rectangle? The function evaluated at the xi bar. Okay, at the xi bar. So again, it's the same. It's the same as the former circumference. Circumference times the height of the ice rectangle, and then the delta x works as the thickness. So it's the same. It's identical with the expression of the cylindrical shell. Okay, so that is the volume for the ice shell. Why we call it the ice shell? Because we rotate the ice rectangle. So similar way, we can cut this region under fx into n rectangles, right? Into n rectangle. You can rotate these n rectangles about y-axis. So you are going to form the n shells. Then you take the volume of those n shells. So that is Vi. Let's continue here. Okay, let's continue here. So this is the way we cut the region. We cut the region into several rectangles, and each rectangle rotating about y-axis. Each rectangle rotating about y-axis, so we get different shell. Of course, it's different because the height of the shell are different, and the volume, the base circle are different, so the volume will be different, right? Then how can we get the summation of all those volumes? Now let's repeat for the ice shell. For the ice shell, this the left one is the one we have already analyzed. So for the ice cylindrical shell, we get the volume formula. Okay, the volume formula Vi, which will be 2 pi xi bar, gives the circumference of the circle with the radius xi bar, and then times the height of the shell, which is the function value which is f evaluated at xi bar, times the thickness delta x. That is the ice shell. How can we get the sum of all those approximating shells? So you take the Riemann sum, right? You take the Riemann sum, let the index I starting from 1 to n Vi. So what are those? So I can rewrite the shell's formula: 2 pi xi bar times f xi bar times delta x. So the n shells, the sum of n shells volume can be used to estimate the volume of the solid. What is this solid we are talking about? So that this V is the volume of the solid rotating about this region. What is this region R? Under function fx, right? And so we can define, actually we can define the V, we can define my V as the limit of the Riemann sum. With the previous knowledge we understand, right, will be the limit of the Riemann sum, which means we increase the number of the shells, that will be more accurate, right? That will be more accurate. Then next question, how can we define the volume as a definite integral? How can we define the volume of the solid as a definite integral? So let's review, okay? Let's review the area part. Let's review the area part. We can define the area as the limit of the Riemann sum, and approaching infinity is the limit of the Riemann sum. We're talking about the area under one function curve. So it's fxi bar or fxi star, it doesn't matter, okay? Here we just choose we specially choose the sample point as the middle point, right? This is one choice of the sample point. So we can define the area A as a definite integral from A to B. What is the integrand? So the integrand is the fx here, right? Is the fx here. So fx dx. So the delta x is equivalent as the dx here. So similar way, we can also define the volume V of the solid as a definite integral. But what is my from A to B here, decided by the lower and upper limit in the curve, okay, from A to B. So what is the integrand inside? 2 pi x times fx dx, right? 2 pi x fx dx. How can we understand this formula? 2 pi x is the circumference of the circle times the height, then times the thickness worked as dx. For example, if the fx as the very beginning, the motivation questions, if my function is 2x squared minus x cubed, then we know the lower and upper limit. So it's easy to evaluate the volume, right? It's easy to evaluate the volume if we know the function fx. So that is the formula we formulated here, okay? So an approximation to the volume of the solid S is given by the sum of the volumes of all those shells, right? So the volume of the solid can be approximated by the sum of n shells, what is this VI, the ice shell? 2 pi xi bar times the height, fxi bar, delta x, the thickness, right? And then we review the area part, how we define the area starting from the limit of the Riemann sum. So we get from the definition of an integral, we can define the volume of the solid as this way. And if the fx is giving us some simple function, then with this method, it will be much easier to evaluate the volume, right? To evaluate the volume. Here, just to make sure A is smaller than B. The lower limit is smaller than the upper limit. Again, how can we understand the shell's volume is circumference times the height times the thickness? Now let me explain here, okay? So again, in the formula, okay, in the volume formula, how can we understand the expression is circumference? 2 pi x is circumference, the fx is the height, dx is the thickness. Now let me show you the example. Let me switch the screen, okay? Let me switch the screen. All right. Now let me show you, okay? It will be a little quick, then we're almost done here, okay? We're almost done here. Did you get a little lucky? So this is like the shell, okay? This is like the shell we are talking about today. This is the cylindrical shell, okay? This is the cylindrical shell. And with the outer radius, this part shows the outer radius, right? You understand it's a shell, right? It's a shell. So we have the outer radius and then the inner radius, right? The inner radius. If you understand the volume of my note, the volume of the note as a cylindrical shell, so the volume of this note will be the outer cylinder's volume minus the inner cylinder's volume, right? So that is the very beginning formula, right? The V2 minus V1, you get the cylindrical shell's volume. Now, how can I understand this one is circumference times the height? If you unfold it, okay? If you unfold it. So my notebook, okay? My notebook looks like a rectangular box. Looks like a rectangular box with a little thickness here. With a little thickness, right? With a little thickness. So that is how we understand the volume of the shell. The volume of the shell will be the circumference which gives the length, right? The circumference which gives the length of the rectangular box. So this length is the circumference of the circle, right? We call the circumference. And then the height of the rectangular box, that is the height of the shell, right? That is the height of the shell. And then this thickness, how can we get this thickness? This is our delta R or delta X, right? This is delta R or delta X. And when we form the circumference as 2 pi x, we know that we can express the radius as x, okay, or xi bar. So in that way, we can, if we know the radius of the circle is xi bar, then we can express the circumference as 2 pi xi bar. And then circumference 2 pi xi bar, height fx, with a little thickness, right? With a little thickness, you can get the volume of the rectangular box. That is the volume of the shell. But we will look at more examples in future. The circumference part, the formula may not be 2 pi x if the radius is something else, okay? If the radius is, for example, if the radius is x squared minus 1, then the circumference will be 2 pi times the radius, x squared minus 1. Make sense? So today we go through the cylindrical shells method and how to understand the definite integral. But to evaluate the volume, it's pretty easy if you know the function fx. Okay, so it's almost time, and I'm going to finish the video here. I will assign the quiz tonight. Okay, I will assign another quiz tonight. All right, I will see you on Friday. If you have any question, contact me on WeChat. Okay, bye.